My name is Gavin Schmidt. I'm a climate scientist and director of the NASA Goddard Institute for Space Studies here in New York City. The key thing that you've got to remember is that we actually have pretty good ideas of what's happened in the past, right? Because we have weather stations, we have ocean measurements, ship measurements, we have lots of evidence of things that are going on. And we know roughly how those systems both vary kind of just on a seasonal or a weekly or an annual basis, and that's what you're seeing when you're looking at the models and the hindcasts for the 20th century. You're seeing, some of that variation up and down, up and down, up and down. But then by the time you get to the end of that century, you're seeing some very clear patterns that kind of come out outside of that noise. And what you're perceiving there is real. So there is noise in the system, and then the climate change signal is just like now it's coming out of the noise. It's actually come way out of the noise and is now very different from what we saw before. And our projections for how that's going to change in the future come from understanding why that signal emerged in the 20th century. And we can go back and we can say, well, was it greenhouse gases? Was it deforestation? Was it ozone pollution? Was it volcanoes? Was it the sun? And it turns out to be mainly because of greenhouse gases. And we say, well, what's the trajectory of those going forward? And you say, okay, well, it's greenhouse gases that are increasing the most, and we're continuing to increase them. The air pollution in the US, that's going down, and the ozone pollution, that's going down, and the deforestation, well, that's getting slower. But the thing that was causing the big change that you saw is also the thing that is increasingly going to become a problem. And so the projections, the skill in the projections comes really from the identification of what's causing the signal and what the amount of noise is. So we might be a little bit wrong in the amount of noise, but the signal is so strong that it's still there, even though this might not be perfectly done. And we know that since that's coming from the greenhouse gases, and the greenhouse gases are continuing to increase, that the amount of noise is still going to become an ever smaller part of the answer. And so when you're seeing things and it's projected out to 2100, and you're seeing like it's all totally saturated in red, well, partly that's just because I chose the color bars that way, but really it's a demonstration that the signal is going to be so clear, is already clear, is getting clearer, is going to be so clear that you don't. The noise becomes irrelevant. Models, famously are all wrong, but the key thing to remember is they're sometimes useful. And judging the skill of the models and where they're useful and where they're not really is a function of going in, seeing how well you're doing stuff, checking it against the observations, seeing how your predictions are working out. But you generally get a sense after a while of what works and what doesn't work. So the things that are very robust, things that don't depend on any particular model, the things that have been evaluated for the 20th century and going forward, are the large-scale temperature patterns in response to these kind of drivers, whether it's increasing greenhouse gases or aerosols or deforestation. Those kinds of things are relatively well, they're well modeled, they're skillfully modeled, and you can kind of have a lot of credibility in those predictions going forward. The things that don't work are more associated with rainfall patterns. There, the models are very sensitive. Lots of different models have different patterns. Things that are associated with very small scale weather events. You wouldn't look at one of these models to get a good sense for what tornadoes are going to do, right? That's too small an event. But some kinds of extremes are well captured in these models, like heat waves. Those are large in extent, they're associated with temperature, and those are actually pretty well predicted by the models. Hurricanes, not so much, right? So hurricanes, you're kind of on the edge. We're starting to get something that's credible, but we're not quite there yet. But how intense rainfall is. That's something that we see in the real world is becoming more and more intense as the amount of water in the atmosphere increases, and those models produce more and more intense rainfall, so more strong rain, less weak rain, and we see that already in the data, and we can predict that that's going to increase. Things like sea level rise, that's a very large scale process. It's more heat going into the oceans, causing the oceans to expand. More ice is melting pretty much everywhere. That's causing the oceans to fill up more. Those are predictions that you can take from these models and say, okay, yes, these are not just qualitatively correct, they're likely to be quantitatively correct. We work for NASA, and one of the things that NASA allows us to do is to pitch instruments for the next platforms that are going up into orbit. We've been working for many years on what's called an aerosol polarimeter, and that is an instrument that would allow us to look through the atmosphere and see the small particles in the atmosphere, and because they each polarize light in slightly different ways, you would be able to tell the difference between particles that came from the dust in the Sahara and pollution particles that come from burning of sulfurous coal. Right now we can't tell the difference. All we can look down on and see is that there is stuff in the atmosphere, that there's haze in the atmosphere, but we don't know what it is. So our ability to model the impacts of that haze on climate, on air pollution, on clouds, really depends very crucially on exactly what particles they are, and we're not in a position to really be able to say that. So we've been pushing very hard for an instrument that would be able to tell us that. We did have one on the Glory satellite, but unfortunately that failed to achieve orbit, and so it's measuring aerosols at the bottom of the South Pacific, which is not doing anybody any good. So we tried that. So that's one of the real key measurements that we need to be taking.